All right, welcome to week 2 of Unit 4 on Earth Science. Right now, you should have your Cornell-style note paper in front of you with those wonderful 3 lines that you're used to. The title for this lesson is Plate Tectonics, and put that on the top. And then our key question that we need to learn about is what happens when the ground moves. So that's going to go along your top line. So here are your key questions to think about. Now, read these. You don't have to write them down, but read them. Try to listen for these answers as we go. What is a plate boundary? What happens at each type of plate boundary? Which boundary causes natural disasters? And what are some famous examples? So we'll start off here. The surface of the Earth seems solid. So as you're walking around and you look at the ground and you walk on it, your feet touch solid ground. What you are not maybe aware of is the fact that the ground is not solid. It's actually broken. And it's broken into a series of pieces. And the word we use for that are called plates. There are a total of 7 major plates and 8 minor ones. Don't worry, you won't have to remember them. If you were in college, they would probably make you memorize them, but we're not going to memorize them. Just be aware that they exist. And when you study the movement of these plates, it is called plate tectonics. By the way, the word tectonic, it's I believe it's from the Greek, maybe Latin. I don't remember exactly, but it is to build. So it's the root word we get, words like technique or technical and things like that. So tectonics is to build. Now, the Earth's plates are made of lithosphere. Lithosphere, as you remember from last week, was the top layer of the crust and then the upper mantle, which is still stone. It has not yet melted. And so you'll often hear these referred to as lithospheric plates or lithified plates. And they're moving because, and they're always moving, and they're moving because of the convection of the magma beneath them. These 4 bullets here, you don't need to write them down yet. I just want to kind of establish that these exist, and then we'll get into more depth. But magma can rip them apart. Magma can sink and then drag them down back into the mantle. Magma can actually cause them to go together. And then magma can have them move basically in opposite directions right next to each other. So to summarize all that, here's a video to kind of drive that point home.
Earth's center, or core, is as scorching as the surface of the sun. All that energy wants to escape like steam inside a boiling kettle. It pushes outward, putting immense pressure on the middle section, the mantle. Standing in its way is the lithosphere, a rigid layer of solid rock. The lithosphere isn't like a smooth shell. It's cracked into pieces, each one a different shape, size, and thickness. We call those pieces plates. The mid-Atlantic ridge is the border between several plates. They're being dragged apart by forces from deep inside the planet. You can think of it like a pot of soup. The Earth's core is the burner, and the mantle is the boiling soup. As the soup near the burner heats up, it becomes less dense and rises. When it gets to the top, it cools off and sinks down toward the heat. In physics, those are called convection currents. A similar process is driving the mantle, and it's taking the plates along for the ride. That movement is called plate tectonics. Plates have been bouncing off each other for eons. The oceans have expanded and contracted. Land masses have smashed into each other and broken apart. Seismic activity is greatest along plate borders, at convergent boundaries where 2 plates collide, at divergent boundaries where they pull apart, and at transform boundaries where they slide past each other. At all 3 boundaries, there's enormous pressure on the Earth's crust. That's the topmost layer of the lithosphere. The pressure can build up for years. The longer it takes to release, the bigger the earthquake. And plate movement drives volcanic activity, too. At divergent boundaries, like the mid-Atlantic ridge, there's a gap in the lithosphere. So magma, molten rock from the mantle, is constantly pushing up along the boundaries. These are the most volcanically active places on Earth. Volcanoes are also common at boundaries called subduction zones. That's when a dense ocean plate converges with a lighter continental plate. The heavier plate gets pushed below, down into the mantle. Some of it melts, and the magma erupts farther inland. The Ring of Fire is a massive chain of these volcanoes. Dense sedimentary rock making up the Pacific seafloor is subducted, transformed into metamorphic rock through pressure and heat, and then recycled as igneous rock through volcanic eruptions. In other words, plate tectonics drives the rock cycle, the constant process of transformation and renewal of the Earth's crust.
All right. So now that's kind of a preview of everything we're going to be doing or learning about. Now let's get specific. Anywhere on the planet where at least two plates are touching is called a plate boundary. So if you think about the word boundary, a boundary, the root word of that is the word bound, and it means to be basically restrained or kept back. A boundary is basically the limit, okay? So if you take a stack of newspapers and they're bound together with string, it's the limit to how far they can go. And so that basically means it's the end of a plate. So a plate boundary just means it's the limit or the end of a plate. And where one plate ends, another begins. So these boundaries are where earthquakes and volcanoes happen for the most part. The vast majority of earthquakes and volcanoes happen near these plate boundaries. Not all. There are some places, for example, Oklahoma is seeing some earthquakes in recent years, partially due to the fracking industry. New York State has had a couple. There's a really big earthquake fault in Missouri that caused the New Madrid earthquake. But for the most part, the earthquakes and volcanoes on the Earth happen on one of these plate boundaries. There are three main types, and then one of them gets divided up in half. So we'll go through them one by one. The divergent is the first one. It's where two plates are pulled apart. Convergent is where two plates are pushed together. And transform, the root word of the word transform, trans means across. So you think of a transcontinental railroad or Trans-America pipeline. Trans just means across. And that basically means two plates are across from each other and they're going in opposite directions. So we're going to go one by one here. The first one is divergent. You do want to draw that diagram. Just do the best you can. You don't have to be an artist, but make sure you have two plates basically moving apart. They're separating or dividing is the way you can think of it. And magma comes up in the middle. So with divergent, I want you to think of the word divide. If I divide two things up, I'm basically separating them. It is usually located, in fact, not usually, always located at the site of an upward convection current. It means magma is pushing up. It causes the two plates to separate, and then magma fills that gap and makes a long chain of volcanoes. And they will often have frequent earthquakes. And the reason why you get earthquakes is because as the magma pushes up, it basically is forcing its way through the ground, and it causes the rocks to shift and things to move. It's very often called a spreading center, and you want to write that down as well. You're going to see the term spreading center again and again. Basically, it's where the ocean, usually the ocean, spreads. It basically separates or gets bigger. That's actually not always in the ocean. On the continent of Africa, over towards the eastern side, it actually is spreading as well, but it's spreading in the middle of the continent, which is kind of unique. But yeah, so think of spreading center. It's literally making, in the Atlantic Ocean's case, it makes the ocean larger. And so speaking of the Atlantic, the famous example is the Mid-Atlantic Ridge. It literally runs from basically the North Pole almost to the South Pole. I mean, thousands of miles of volcanoes, and it's right now causing the Atlantic Ocean to grow. The Atlantic Ocean right now gets bigger about an inch per year. So that means if you're 15, 16 years old, the Atlantic Ocean is now a little bit more than a foot wider than it used to be when you were born, which is slow, but it's significant and it's measurable. So now let's visit the Mid-Atlantic Ridge.
But while some plates crash together, others tear apart. It happens under the ocean. Like here, in the middle of the Atlantic. Lava erupts at the boundary between two crustal plates, sealing the tear. This is the Mid-Atlantic Ridge, a 10,000-mile tear on the floor of the Atlantic Ocean. The ridge is a line of underwater volcanoes, and it's here that new oceanic crust is formed. It stretches from the South Atlantic all the way to Iceland in the north, where it rises above sea level. From the air, the Mid-Atlantic Ridge is an awesome sight. This dramatic scar in the landscape marks the boundary between the North American crustal plate on the left side and the European plate on the right. The gap between ocean plates is filling in at a rate of an inch a year. Part of the restless movement of the Earth's crust that's reshaping our world.
So the opposite of a divergent boundary, it sounds exactly the same, but this is called a convergent boundary. Now, convergent boundaries come together as opposed to separate. It's usually located at a downward convection current. So this is a place where the lava has been cooling for a while and starts to sink. Because it's cooling, let's recap. When it's cooling, it's getting more dense. More dense things sink. So what typically happens is you get two plates that are colliding. They're hitting each other, and then one with the greater density or the higher density, it sinks back down into the mantle and it starts to melt. Now, as it melts, it becomes less dense. Things that are less dense will start to rise. And when it rises, it finds cracks and openings in the lithosphere above, and it creates brand new volcanoes. Typically on the what's called the overriding slab, or what that means is the section of plate that was on top and did not sink. This can be oceanic crust, or it can also be continental crust as well. It typically makes an island chain because the plates of the Earth are long. They're miles and miles long. So you get multiple volcanoes from different melting sites. A couple of examples. One would be the islands off of Asia. So the Philippines, Japan, all that. And then the other one would be off of Alaska, the Aleutian Islands. Now you're going to want to write down the word subduction zone. The subduction zone is the actual place where it is going under the other plates. So the way to help you remember that is, think of a Navy ship that goes beneath the water, and that's called a submarine. So if you can remember submarine goes beneath the water, or the surface of the water, you can remember that a subduction zone, subducts means going under the other plate. So they have very, very large earthquakes and very dangerous volcanic eruptions. So this is definitely one that is much more of a danger than divergent. And maybe the most famous example of a really deep subduction zone is the Marianas Trench, also often referred to as the Mariana Trench. I don't know why. Sometimes there's an S and sometimes there isn't. But it's located off the coast of Asia, and it's the deepest place in the ocean. It's called the Challenger Deep, and it's 36,000 feet. And now we'll visit there.
Surface, LF, depth 109 or 28 meters.
Okay.
Men,
Okay, roger that. We'll go for a release. That's all.
life support, good. Depth 109 or 28 meters. At bottom, repeat, at bottom.
At the bottom?
Yep.
Roger, LF. Understand you are on the bottom. Congratulations, Victor. Congratulations.
Well done. Beginning exploration of the bottom. Well done.
You did it, buddy.
Well
You
done.
did it.
We all did it. We all did it. Captain Walsh. Thank you. Thanks for showing the way. Thank you. Oh, you're mine. It was an amazing experience. It was an amazing dive. I think almost exactly 12 hours, about 3.5 down, 4 hours on the bottom. I think the longest anyone's ever been on the bottom of the Challenger Deep, and then about 4 hours up. I went through pretty much all of my electrical power and had to be swapping batteries around and circuits around. It was a great journey. Saw some really interesting things on the bottom.
So there's another type of convergent. It's similar in that the two plates are still moving towards each other, but it's not the same because they both have the same density. And when they both have the same density, they hit each other and neither one will sink. If neither one sinks, they start to move upwards. And so as they start to move up, since they can't go down anymore, they're still floating on top of the mantle, they create a gigantic mountain range. This is called a collision boundary. This is not common. There's only a couple in the whole world, but the best example of that is Mount Everest. Mount Everest, the tallest mountain on Earth, you probably have heard of it. Mount Everest is on a collision boundary between the Indian plate and the Eurasian plate, and it's literally growing every year. So the two plates keep moving towards each other and smashing into each other. And as a result, Mount Everest grows. And Mount Everest is growing at, about the same rate as the Atlantic Ocean is spreading. It's about 1 inch per year. And that means that, again, if you're a teenager, Mount Everest is now a foot taller than it was when you were born. And that's actually something we can measure, which is kind of neat. And the last, this is a transform boundary. This is the one that's relatively close to your house. We'll get there in a second, but it is where two plates are across from each other. They're touching, but they're going in the opposite direction. One's going east, one's going west, or one's going north and one's going south, whatever. And what happens is they slide past each other. And as they do that, they're kind of grinding the rocks and layers are grinding next to each other. Anytime that they get stuck, they start to create a mountain range, what are called folded mountains. And then eventually they release, they snap. And when they do that, it releases a bunch of energy. And we call that an earthquake. You guys are familiar with earthquakes. You've probably felt one in your life if you lived here for your whole life. The earthquakes created by transform, though, are not as powerful or as have as much energy as a subduction earthquake. There's many reasons for that. The main reason is when subduction earthquakes occur, they occur over a longer fault and they occur with a tremendous more or greater amount of elasticity. And we'll learn about that next week or next lesson. The most famous example of a transform boundary is, of course, the San Andreas Fault. You've probably heard of it. Most people who live in California have heard of it. It is located here in California, and it basically unites, or not unites, but it's the barrier between the Pacific and North American plates. And so there are places in California where literally you can have 1 foot on the North American plate and 1 foot on the Pacific plate, which is kind of neat. So let's take you to the San Andreas Fault.
These giant gashes in the Earth are reminders of our planet's awesome power. They are fault lines, fractures in the Earth's crust where huge slabs of rock slowly grind past each other. Most faults we can't see, but here in California, the San Andreas Fault is visible at the surface.
You can't have an earthquake without a fault. And I'm standing right now on what is perhaps the most famous fault in the world, the San Andreas Fault, that extends from Mexico down south, way up to Oregon in the north. This is one of the few places in the world where you can stand with 1 foot on one tectonic plate and one on another. In other words, this ground here is attached to New York and Iceland. The ground here is attached to Hawaii and Japan.
The San Andreas Fault sits on the boundary between the North American and Pacific plates. It's called a strike-slip fault, a place where two plates collide and try to slip past each other. As these plates move or creep in different directions, sometimes they get stuck. The longer they stay stuck, the more tension builds and the bigger the eventual quake. In other places, the plates move smoothly past each other. These areas buckle as the Earth shifts. The changes are subtle. Roger Billam keeps track of these changes with his creep meter, a device that measures movement along the fault. A computer collects data every minute for a year. This jump in the graph tells him the Earth shifted about 5 millimeters in a couple of hours. A small shift like this can have huge consequences for us.
That might not seem much, 5 millimeters, but it's affecting a long section of the fault, maybe 5 miles long, involving millions of tons of rock. Now, it really doesn't matter here. This is a nice sort of field, there aren't any people, but further north, this creep process and the things that are happening beneath the Earth are far more sinister.
The San Andreas Fault and its branches trigger more than 10,000 quakes a year. Sometimes the results are devastating. Just ask the people of Los Angeles or San Francisco. Over the last 2 decades, major quakes rocked both of these cities. Life goes on, but the risk remains. In an area this active, the next violent tremor could happen at any time.
All right, so now I'm going to show you a series of pictures. I want you to, based on what you've now learned, I want you to try your very best to identify them. So let's take a look at this guy right here. Ask yourself, do you know what type of boundary this is? There are 4. Please tell me, or don't tell me. Ask yourself, and then I will give you a few seconds, and then I will reveal the answer. So this is called a subduction zone. As you can see, it is sinking on the left. The oceanic crust is sinking or going down beneath the overriding slab, and it is subducting. And so it's creating a volcano above. So there's a subduction zone. How about this one? Ask yourself if you know this one. And this is a transform. Notice how the 2 plates are across from each other. They're moving in opposite directions, and they would be in the middle right there, sliding and grinding next to each other. And observe how the entire lithosphere and then the very top of the asthenosphere are all moving in the same direction. So this is what makes it so that the people have told you California is going to fall in the ocean. It's not true. The entire section of land here is moving in the same direction. So we're safe from that. And the last one, what's this? And hopefully you were able to figure out this is divergent. As you can see, 2 plates are separating. Magma is coming up to fill the gap. Notice how there is a little thin red line in the middle of those 2 plates. That would be your line of volcanoes. So now ask yourself, do you know the answers to these key questions? Do you know what a plate boundary is? Do you know what happens at each type of plate boundary? Do you know what are the boundaries that cause natural disasters and which ones are worse than others? And finally, what are some famous examples of plate boundaries? So what I want you to do right now is put these notes aside, come back to them later, try your best to write a summary without checking your notes. But if you can't, you can look back, but write yourself a summary. And once you're done, you've completed this lesson. And as always, thank you for your attention.